All right, so we've had a look at axial stress, which is direct stress, and now we're going to have a look at the one of the other main types of stresses, which is shear stress. So, in defining shear stress, well, let's look at it relative to a direct stress or an axial stress. So, as we saw previously, direct stresses act normal to a surface. So, if you're pushing on a surface, they're going to act. Those stresses are going to act perpendicular, so normal to that surface. So, conversely, shear stress is going to act tangential to the surface. So, it's going to give a shearing, or it's going to try to turn. So if a direct stress is trying for, and compression is trying to squash, or if it's in tension, it's trying to pull apart a section, a shear stress is trying to take a square and turn it into a parallelogram. It's trying to do, you know, oh, this was actually trying to go like that. All right. And so, well, let's have a look at shear stress, similar to how we did with axial stress, and have a look at how it's defined mathematically. Um, so to do that, let's start with our little block here. So we have an element, um, and it's prismatic, it's rectangular in nature. And it's going to have a force pulling on it to the side, and we'll call that force V. To make this in equilibrium, well, it needs another force at the top, also V. Now, we won't worry about the moment here at the moment because that's a little bit confusing at the moment for us. So we have this force at the bottom V, and this force at the top also V. So let's look at a section right in the middle and just draw this free body diagram. So at the bottom, we have our section here and our force V. Now, if we want to find the stress, just like we did with axial stress, we essentially broke up this surface into lots of little sections. And we look at, say, one little section. So we want to find what the stress is at a point Q. So at this, say, this red point, we'll give that section some area, call it delta A, and it's going to have some tiny little force in there, delta V. And just like with axial stress, if we want to find the force at this very central point Q, essentially what we need to do is make this area smaller and smaller and smaller. So the shear stress at a point is going to be very similar to the axial stress, but instead of acting normal, it's going to act tangential. So shear stress, and we give shear stress the Greek letter tau, and that's going to equal the limit as delta A goes to 0, delta V, delta A. So this is, yeah, it's a shear stress at a point, and if we want to find the shear stress over the surface, well, we can use calculus and we can integrate over that surface. Now, while a lot of the axial stress method, well, sort of instances that we saw, there was a lot of opportunity where we could assume a nice even average stress, and that was a good assumption for what the actual stress state is in the member. That is not the case for shear stress. So, it's worth even just writing down that shear stress is not uniform. In fact, it tends to vary parabolically. And so what I'll do is I'll show you a few different stress distributions. Um, and you can see there's some cases, so much like with our axial stress, there were some instances in which we had very huge differences in stress profile across the width of the section, and there's some where we didn't have as much. And where we didn't have as much, being able to use the average stress was a good approximation. And as engineers, particularly if we're doing design where we're going to iterate multiple times on to try to find out, well, what's the best solution, we need to have simple analytical tools which we can use over and over again and aren't going to be big complex things for us to work out. But we need to make sure that those simplifications are close enough to reality that the way we're using them in design is going to be appropriate. So what we're going to do is we're going to look at, just these few sections. So the first one I'm going to look at is a rectangular section. And essentially for these shear stress profiles, what we're going to do is, imagine it's a prismatic section. It's got some neutral axis. And what we're going to do is we're going to plot what the stress distribution is over sort of that volume of stress, and then we'll just look at it from sort of a section and then a cross section view like this. So for a rectangular section, we have our neutral axis here. And then if we look at what the stress profile is, our maximum is always at the neutral axis, and our shear stress is always 0 at a free surface. Now, I don't expect you to know that at this stage. Just readjust the camera here. We will go over this in a lot more detail in the coming weeks, but it's I think it's useful to show you some of these things sort of as coming attractions, so that it helps you sort of get some conceptual understanding. So if this is the section, this is our shear stress profile. If we want to look at an average stress, it's really a rectangular profile. We'll call that tau av. And that's just and this is just like with our direct stress, our axial stress, we're assuming that is our stress V over A. And if you work out the math, you'll find out that tau max equals 3 over 2 tau av, which equals 3 over 2 V over A. So what this is saying that is our maximum shear stress we can expect is going to be 50% larger. So 3/2 times this average we would assume just by taking the area. So that, having a discrepancy of 50% is pretty large. And so that means this isn't a very good assumption for design, which is why for rectangular cross sections, we don't use this V over A. Let's have a look at a few others which are common, and then we can see, is there a pattern? Is there at any point where this assumption seems to be pretty good? And as I said, we'll go over how to define this profile in the coming weeks. So don't worry about that for now. So instead, if we look at a circular section, So if that's our section there, neutral axis in the middle, and then we'll just plot what our shear profile looks like. Again, we're maximum at the neutral axis, and we're parabolic. But what's interesting here is that our average shear stress is, so this is tau av, and this is tau max. If you work out the math, you'll find tau max equals 4 over 3 V over A. That's a lot closer. So instead of a 50% discrepancy, we only have a 33% discrepancy. It's still not bad. It's still not great, you know. It's a bit of a rough estimate, but it's a lot better than for a rectangular section. Let's look at two more. Let's look at an I section. So for an I section, we'll draw it out here. And mind you, this is going to be an I section which is loaded parallel to the web. So if that's our neutral axis, and we'll bring across just some points so that we can look at our distribution, we'll find that we have a small distribution, again parabolic on the flanges, but then when we get to the web, something interesting happens. It shoots way up, and tau max is still at the neutral axis. But if we look at the area of just the web, so we can see, you know, if we have tau average equals V over the area of the web, that's actually a pretty good assumption of what our maximum stress is going to be. And in fact, you'll find that for a lot of steel codes, they say, well, you can assume your tau max is approximately tau average equal to V over a web. So that's kind of neat. You know, that seems like that's a point where we can use a fairly simple equation. Because I mean, if you look at this profile, that thing looks like a mess. You don't want to have to calculate that for each and every section, particularly if you're doing a design and you start with a section and it might not work. You don't want to have to go through big complicated calculations all the time. So that seems like that's an interesting point that we might be able to take advantage of. And let's look at one more. Let's look at a T section. So this is our T section. Our neutral axis is going to set up a bit higher towards the flange there, and you find out you get a profile that looks something like this. Tau max. So you can see pretty clearly that for a T section, you don't have anything that looks sort of nice and rectangular and average. So tau max is not anywhere close to V over a web. So if we just zoom out here a little bit, we can notice some patterns. So for our shear stress, sorry, zoom out again. For our shear stress, it seems to vary parabolically. Our maximum shear is always at the neutral axis. Shear at a free surface is always 0. And there seem to be some cases where we can, make an assumption that the average shear stress, just a force over an area, is a good approximation for what our maximum shear stress is. So, I sections loaded parallel, and actually circular sections aren't too bad. And that's where you'll see in a lot of steel codes, these are the two which they allow you to assume V over AW. So what we're going to do, and for a little example, is look at a circular section. It's going to be for bolts and shear. And again, keep in mind that we're going to use V over A, but it's not 100% correct. But oftentimes for bolts, you've got some additional capacity there, and you need something, kind of quick for the analysis. And oftentimes, your shear stress is not going to be your critical aspect for that connection. So those are some of the reasons why we can get away with using it. Also, we only have about a 30% discrepancy, where for a rectangular section, it's definitely not going to work for us. So with that, let's just have a quick look at some bolts in shear. So bolts in, we're going to call it single shear. So in single shear, what we have is we got our bolt here. So it's got the hex head, and then it's got the bolt shaft, and then we'll assume that the root, so the area which is neck down where the threads are, is all sitting within the nut, just for this example. And then if it's single shear, we really just have two plates acting on it. So we've got a plate on the top that has a force pulling on it, and we have a plate on the bottom, which also has a force which is pulling on it over here. So as these two are pulling apart, what they're doing is they're trying to deform this bolt and to shear it off, to like guillotine it off. So let's draw ourselves a little free body diagram. So if this plate is, and we'll take the cut kind of, we'll do our cut in red here. We'll take it right through this top bit here. So remember, if we're pulling here, well, pulling on this plate is just like this plate pushing on this back end. Because remember, this is a hole that we've sort of sliced through. So our free body diagram looks a little bit like this, where you've got this force, and you have this shear V. Remember, this is a free body diagram of the bolt. And so with that, again, for everything to be in equilibrium, we know that F has to equal V. And so, as I said, for circular sections, T average is an okay approximation. So T average equals V over A equals V over pi r squared. And you notice we only have one shear plane, and this is why we call it single shear. So we have one shear plane. All right, so the other very common case for bolts is, so we have single shear. Oh, well, we have double shear. So if you've got a bolt in double shear, So if we had one shear plane for single shear, you can bet that we've got two for double shear. And that means that we have really sort of three plates acting on it. So we'll draw our bolt again. That's the threads on it. And these are our plates. So we've got one in the middle. Which is getting pulled. And then we've got two on the top and the bottom. So we'll call this one F. We'll call this FA and FB. And we'll just hash in those plates just to make them a little easier to see. All right, so here again, we'll take another little free body diagram and we'll cut right at this surface. So we're going to look at the bolt and we're going to look at the shear in the bolt here. So if we have this force pushing this way, let's draw our free body diagram the same. So you've got a force pushing here, and then you have a shear force top and bottom. So the shear force is going to be equal because we're equidistant. And then since everything has to be in equilibrium, you find that we'll call this V1, V2. So V1 equals V2, V1 plus V2 equals F. And so V equals 1/2 of F. And then we can then look at what our average shear is across there. Tau average equals 1/2 F over A, and that equals F over 2A. And that makes sense. So you've got two shear planes. You have twice the area which you're trying to stress. And remember that your stress is going to be proportional to your area. Double your area, you're going to half the stress. So you've got two shear planes on our double bending. There we go. And so that's our sort of introduction to shear stress. As I said, we're using average stress here. And it's really only going to be applicable for these special cases of bolts in shear or an I section which is loaded parallel to its web like we have here. So those are our two cases, and we will explore shear in more detail, and we'll look at the cases where you have non-uniform profiles which occur very often, and they're not that big of a deal to contend with. So with that, that's going to wrap up our introduction to shear stress.